If the encoder in a transformer is responsible for understanding the input sentence and generating its representation, the decoder's role is to generate the output sentence based on that information. In this process, the decoder uses masked self-attention to prevent access to future information and cross-attention to interact with the encoder's output, enabling it to produce more accurate and natural sentences. In this video, we will take a closer look at the decoder structure, one of the core components of the transformer.
The part highlighted in red here is the transformer decoder. Like the encoder, the decoder is built by stacking n layers with an identical structure, and in the original paper, 6 layers are used for both the encoder and the decoder. Each decoder layer consists of 3 sublayers. First, masked multi-head self-attention is applied to prevent the model from seeing future tokens. Next, multi-head encoder-decoder attention allows the decoder to attend to and make use of the encoder's output representations. Finally, a feed-forward network is applied. As with the encoder, residual connections and layer normalization are applied to the output of each sublayer. The output of the final decoder layer is then passed through a linear layer and a softmax, producing a probability distribution over the next token to be generated. The transformer processes an entire sentence at once using a parallel architecture. Because of this, in the encoder, all words in a sentence are allowed to freely attend to one another, including words that appear later in the sentence, enabling the model to capture full contextual information. The situation is different for the decoder. In tasks such as translation or text generation, where words must be generated sequentially, it is not allowed to look ahead at future words that have not yet been generated. For example, when predicting the word better after I like baseball, the model must not have access to that future word in advance. If the model were allowed to see the correct answer beforehand, it would effectively be cheating during training. To prevent this, the decoder uses masked multi-head self-attention. This mechanism enforces causality, restricting each token to attend only to itself and to past tokens. In other words, past words can be used for prediction, but future words cannot. Now, let's take a look at how masked multi-head self-attention is implemented mathematically. In standard self-attention, the scaled score is computed from the dot product of the query and the key, as shown in the equation below. In the decoder, a masking matrix M is added to this score. Here, I denotes the position of the query, that is, the position of the word currently being predicted, and J denotes the position of the key, or the word being compared. The masking matrix, M, assigns negative infinity to the score when the key position J lies in the future relative to the query position I, and 0 otherwise. When the softmax function is applied to these masked scores, the values corresponding to future positions are pushed toward negative infinity, causing their probabilities to converge to almost 0 in the softmax output. As a result, future words are effectively excluded from the attention weights and contribute nothing to the construction of the current token's representation. This masking is applied independently but identically across all attention heads. Each head learns information from a different perspective, but the constraint that prevents access to future information is shared by all heads. In the end, masked multi-head self-attention follows the same computational process as standard multi-head self-attention, with the only difference being the additional masking step introduced to block future information. Based on the self-attention computation process we examined in the previous encoder video, the decoder's masked multi-head self-attention differs only in that an additional masking step is introduced. The overall computation flow remains the same. Using query and key matrices of size 4 by 64, a dot product is performed, followed by scaling to produce a score matrix of size 4 by 4. At this stage, a masking matrix is added to the score matrix. This masking matrix is designed so that scores corresponding to future positions are assigned negative infinity, while scores for past and current positions are assigned 0. When the softmax function is applied to these masked scores, the probabilities at positions corresponding to future words converge to 0. In other words, the current query can attend only to itself and to past words, while future words make no contribution at all to the attention. Next, let's look at encoder-decoder attention, another key component of the decoder. For example, the encoder takes the Korean sentence as input, and the decoder generates the translation, "I like baseball better," step by step. At the point where the decoder has generated "I like baseball," it is not allowed to refer to the yet-to-be-generated word better. This restriction is enforced by the masked self-attention mechanism discussed earlier. Separately from this, however, the decoder can attend to all encoder inputs, "I like baseball better," and assign higher attention to the most relevant words, enabling the correct translation. In a transformer, encoder-decoder attention, also called cross-attention, is a key component that connects the encoder's output with the decoder's input. In tasks such as machine translation, the decoder cannot produce a meaningful translation unless it refers to the semantic information extracted from the input sentence by the encoder. For this reason, the decoder needs a mechanism that allows it to selectively attend to the important information in the encoder's output. This becomes clearer when we compare cross-attention with self-attention. In self-attention, the query, key, and value are all generated from the same sentence, allowing the model to learn relationships among words within that sentence. In contrast, in cross-attention, the query comes from the decoder, while the key and value come from the encoder's output, allowing encoder information to be directly incorporated into the decoder. Now let's take a closer look at how the query, key, and value are constructed and computed in encoder-decoder attention. As shown in the figure, the sources of the query, key, and value are different in encoder-decoder attention. While the process of generating Q, K, and V by multiplying each input with its own learnable weight matrix is the same as in self-attention, the key difference lies in where these inputs come from. Here, K and V are derived from the encoder's final output, whereas Q is generated from the output of the decoder's masked, multi-head self-attention. As indicated by the arrows in the diagram, although Q, K, and V originate from different sources, the subsequent computation follows exactly the same steps as in self-attention. This encoder-decoder attention is also extended to multi-head attention, allowing multiple attention heads to learn encoder-decoder relationships from different perspectives simultaneously. Now, let me explain the feed-forward network. The FFN is placed after the attention sublayer and is responsible for applying a nonlinear transformation. Structurally, it is a position-wise MLP consisting of a linear transformation, a nonlinear activation, and another linear transformation. First, each token vector X, after passing through the attention and add and norm steps, is multiplied by learnable weights and biases to map it into a new feature space with a different dimensionality. Next, a nonlinear function such as ReLU or GLU is applied, allowing the model to learn complex relationships. Finally, another linear transformation is applied to produce the final output vector. This process is applied independently to each token. That is, if the inputs are x1, x2, the outputs are generated as FFNX1, FFNX2. Next, let's take a look at add and norm. This structure combines residual connections and layer normalization, and it is applied after each attention or feed-forward sublayer to stabilize training. First, in the residual connection or the add step, the input x of the sublayer is added to its output f of x. This helps prevent the loss of important information as the data passes through multiple layers. Next, in the layer normalization or the norm step, the summed result is normalized, which stabilizes the training process. In short, using add and norm together ensures both information preservation and training stability. Let's take a closer look at residual connections and layer normalization. First, a residual connection is a structure in which the input x of a sublayer is added directly to its output fx, where fx is the output of either the self-attention module or the feed-forward network. As transformations such as attention and FFNS are repeatedly applied, input information can be lost or distorted. Residual connections help prevent information loss. Next, layer normalization normalizes each token vector based on their mean and variance. By normalizing the combined output x plus fx from the residual connection, layer normalization helps make training faster and more stable. In summary, using residual connections together with layer normalization allows the model to preserve important information while simultaneously ensuring stable and efficient training.